Part of 5.4 of the central limit theorem is there is a simulation to kind of get an understanding a little bit about what it means to do a sampling distribution of the sample means. So in your coursework, if you go down below final, you should see this folder, MyLab Statistics. If it open it up, if I scroll down through there, we should see this MyLab Statistics Multimedia. So if I open that up. So in chapter 5 and 5.4, there's an applet called a sampling distribution. So if I get that opened up here, let me get that out of the way now. So we can bring that over here. Oops, too far. So what I can do with this is I can do what's called a sampling distribution. So right now, notice how it's a uniform distribution. What I can do is I can kind of make a continuous custom one by just kind of just drawing it, freelance it if I want. It doesn't have to be like bell-shaped curve to start with. That's the cool thing about the central limit theorem, is it doesn't have to be a bell-shaped curve to start out with. So let's set my population as a mean of 25.9018 and a standard deviation of this 12.1518. So the sample size, let's just start with a 5 to start with, to kind of make it go slow. So what I want to do is just run the simulation one time. And what it will do is it will grab randomly 5 values from our population. It'll bring these 5 values down, and then it'll do a mean of those 5 values. So if I do that one time, it'll grab 5 different values randomly, and it'll do the mean of that sample. So if I do that again, it'll pull out another 5 values, and it'll do another sample mean. And I could just do that on and on. So if I do that, say 5 times, it'll pull down those 5 values, and it'll calculate 5 sample means. So we're now up to 7 times. So we've actually pulled out 7 samples of the size of 5, and we have 7 sample means. So notice how we really don't got a whole lot going on until we really do this a lot of times. So as we do this quite a few times, so if we jump this up to 1,000 times, notice how we start to take on the shape of a normal distribution. Notice that our mean is this 25.9018. The mean was, the standard deviation was this 12.158. Notice how, if I look at my sample means, notice how our sample mean is kind of close to the population mean. If I look at our standard deviation, notice our formula for the central limit theorem is, if I have the known standard deviation, which we have is 12.1518, if I divide that by the square root of the sample size, so the square root of 5, it'll give me the standard deviation of this 5.434. So notice how we're getting a standard deviation that's very close to that. So that's the really cool thing about that formula, is it allows us to find the standard deviation of the sample means with a real quick formula. Now, if I do this another 1,000 times and another 1,000 times and another 1,000 times, notice how we're getting our bell-shaped curve going on down here for our sample means. Now, if I want to, I could reset this and change my sample size to maybe like 50. So now if I do this one time, it's going to randomly pull out 50, and it's going to do a mean of those 50 values, and I get one sample mean. If I do that 5 times, we kind of get that going on. So I've now have done that. I have now 6 sample means. But again, to really see what happens here is you really have to do this a lot. So if I do this 1,000 times, notice how, again, it starts to be a bell-shaped curve. Notice how, again, my mean is very similar. Notice how I have 25.9018. Notice how we have 25.9046. And notice I didn't have to do as many times either. I just did that 1,000 times and it already has got my mean really, really close. Notice that my standard deviation is much tighter too. Notice how my bell-shaped curve is much closer together. It's not as spread out. That's another thing about picking a bigger sample size. It's going to make the standard deviation much, much smaller. And again, if I use my calculator, notice that again, I could use that standard deviation of 12.1518. If I divide that by the square root of that sample size of 50, notice how I do get the standard deviation of the sample means. Notice how it's really, really close, 1.732, and this is the 1.718 or 1.719. If I did that another 1,000 times, notice that we're getting our mean is getting, everything is getting much tighter in that situation. So we can, and I can keep doing it 1,000 times again if I want. Notice that 3,000 times, it's very, very symmetrical. It's very balanced at this point. So it's looking really good as far as things go. So you kind of start to see that bell-shaped curve happens. So that's what that's saying is, if you don't have something that's normally distributed to begin with, if you have a sample size of 50, the sample means is going to be a normal distribution. And since it's normally distributed, then all the bells and whistles go along with that. So we can use all the formulas that go with the normal distribution curve. So we can do z-scores. We can find the area under the curve and those probabilities that all align nicely with this formula. So it allows us to do a lot of math with this powerful formula in the central limit theorem. So hopefully you find that kind of useful in what we're talking about here. So again, we have our samples. So we have a sample size of 50, but notice how we did that sample size. We calculated 3,006 sample means. And when we did that, our means, notice how they are getting really, really close together. And by definition, they're actually equal. So the population mean and the mean of the samples will be the same value. But the standard deviations, notice how the standard deviation here was 12.158. But notice that the standard deviation of the sample means, the bigger the sample, notice how our sample size is 50. Notice that our standard deviation got much, much tighter. There was not as much variation from the mean. So again, hopefully you found that useful moving forward into the central limit theorem.